Okay, can you guys hear me now? Excellent. So my mic has been doing that recently. Don't know why, it just glitches out. So definitely let me know if you can't hear me, because that is 100% just an issue on this end. I don't know if the microphone is actually dying or if it's coming unplugged from my computer. One of the two. But anyway, so to recap, type 1 or weak induction, you're given some statement. Your basis step is you literally just pick the smallest value for n that you have in your equation or your inequality. You plug it in, you check to see if the thing still works. That's literally it. Okay? So the second step has two parts. Ooh, I don't want red. And the first, so this is the induction step. And the first part of the induction step is really you just assume everything works. So assume works for n equals k. Okay? K is an arbitrary letter. I would definitely recommend using the letter K here just because, well, it's going to make your life easier in the future. Okay? So you say, all right, we're going to assume somebody else has already checked this for arbitrary K. The second part, and this is really where all of the work happens, is this is where you would show that your statement works when n equals k plus 1. So the next one that hasn't been checked yet, the next n value that hasn't been checked yet. And here's one of the key things, and let's actually highlight that in a different color. You're going to want to use the fact that we already assumed the statement worked when n equals k. Okay? Please note those capital P's, they are 100% just notations, notational conventions. It is not what you'll actually see. I'm writing these new, but yeah, this was exactly the same thing that we had at the beginning of last period. I just recopied it mainly because I didn't pull down what we had from last time. Okay. All right, so that's the weak induction. Here's the new part. So type 2, or as your author calls it, strong induction, is almost exactly the same. And there's also a handout, it's handwritten, but it's a PDF file on this stuff that writes out all of this as well. Probably a little bit more technical than what I'm doing right here, just because I wrote down all of the little details. Okay. So type 2. First thing, you're still going to be given some statements. So given, and I'm going to go ahead and just say statement P of n, so that predicate statement for n greater than, it can be greater than any integer you want or any integer that works for the formula. I'm going to put a 1 here, not because it always is a 1, but just so it's easier to latch onto when you're thinking about it. The basis step, still almost exactly the same thing. So here you're going to check to see if your smallest n's work when you plug them in. So check if smallest n works. Now I left a space between n and works on purpose because typically with type 2 induction, you don't just check the smallest n, you have to check the smallest couple n's. So I'm going to put an s here, making that plural, and I'll show you in just a sec how you decide how many of those n's to check. It's typically somewhere between 2 and 3 that you have to check. So that's basis step. Notice it's exactly the same as before, except now you're forced into checking a couple more cases. Now the induction step, this is where you actually have the difference between type 1 and type 2. And it's not in B, it's not in 2B, it's actually in the 2A step. So A, we are going to assume that your statement works. Notice so far it's the same. For all n, that either equals that special guy K and everybody less than K. Not going to lie, the way that I've described regular old induction to you guys in the past is really describing type 2 induction, where you do it in a very systematic way. You start with your smallest value for n, you check the couple of them, then you go up and assume somebody else has checked a bunch of them, and then K is the last n that somebody else has verified. That's really strong induction. And in fact, you can always use strong induction, just skip out on the weak induction if you want. And then part B here, the main part is, again, do the same thing. You show that your statement, your Pn, works for n equals K, no change there. Here's the only difference, and this is the part that makes it induction, is you'll be using the when n equals K and at least one other. So if you had to use more than one previous statement when you're proving the statement when n equals K plus 1, that's when it switches over to strong induction. Okay? So, not going to lie, if you've never dealt with an induction before, and I'm assuming that most, if not all of you, have never dealt with induction before this class, this can be snarly to see when it's just in the formulas or just in the statements. So let's look at an example here, and we'll go through the example like we normally have. So normal old induction, just like we would have last time in our 2.5 examples that we did. And then we'll get to a point where we're going to have to convert it to strong induction, and I'll show you how you tell. All right, so here is our example. And it's actually a great example to lead into our next topic. It's one of the reasons why induction and sequences are typically done next to each other. So suppose you have the following sequence. So suppose you have sequence, and the sequence's formula, or its closed form, is given by formula an equals 3a with the subscript n minus 1 plus 4 times a with the subscript n minus 2. And we are told that the first two entries of the sequence are 3 and 2. Now, before I go any further, do we need a slight aside on what all those symbols mean? Is everybody okay with how I've written this sequence right now? Okay, that response was not super definitive and encouraging. So how about I do a slight aside and we talk about the notation real quick just to make sure we're all on the exact same page. So I actually prepped this up for us because I couldn't remember if we talked about sequences previously or not. And if we had, it hadn't been very much. All right, so I'm going to share this new thing. And we'll come back to induction in just a second. But I wanted to give you the quick crash course here on sequences, and then we'll jump into going back to finishing up induction. Oh, I did not need to do that. Oh, well, it happened. All right. So a sequence, to remind ourselves, is just a list of numbers. We've totally dealt with sequences before when we did counting. We just didn't really focus into all the technical details. So the sequence is literally just a list of numbers. Order matters here. So it matters who came first in the list, who came second in the list. notice when we were dealing with counting, what did we do? One of the things we built were lists of things. We were really building little sequences. Okay? We built finite sequences in the past, and that was a sequence where you actually stopped. We're now going to be looking at infinite sequences, and that's a sequence that it keeps going forever, and how you can tell is you have these ellipses, these dot, dot, dots at the end. Okay? So for example, on this guy, you got 1, 4, 9, 16, 25, 36, etc. Anybody have a guess who the next guy would be in the sequence? So when their sequence is written out just as a list, you write out enough of the terms so that you see a pattern. In this case, you can say, hey, your next term is totally going to be 49. And in fact, you could actually say, what? All of those guys look like they're what type of numbers, if you were trying to describe this more like a formula. Anybody have a guess? Yep, so they all look like perfect squares, or if you wanted to be fancy, maybe you called it n squared. I don't think n squared is going to fly up here. Nope. You could also have guys that are more fractional. This is pretty common to have some sort of fractions involved too. So here, 1/3 is the first term, second term 2/5, 3/7, 4/9, 5/11. Anybody have a guess what the next term would be here? Again, don't overthink it. I didn't try to make these complicated. But sequences are all about finding patterns. Okay, so the top of the fraction was 1, 2, 3, 4, 5, so the next one would be 6. And the bottom, these guys were what? You could think of them as either all odd numbers or going up by 2 each time, so this would be 6/13. So you guys were getting to the right answer there. Okay? And if you wanted to keep going, the next one would be what? 7/15. Okay? So that's all sequences are. They're literally lists of numbers where you try to find the pattern. Now, here's the interesting part. When you try to find the pattern of the sequence, it turns out that there's 2 different ways that you can write your formula for the sequence. One of the ways is called closed form, and your closed formula is literally just a function. If you plug in, say, n equals whatever term number you want, you'll get back immediately that term. The other one is called recursive form or recursive equation or recursive relation, which is our next topic, and that one actually describes your current term in terms of the previous terms. Okay? So there's 2 ways to do this, and they're about to fly in. Okay? So if we want to find this formula or this rule, we have to know something about terminology, and this is why I jumped to these slides, is the terminology. Okay? So basic terminology here is you're going to have some letter. It doesn't have to be A, but A is the default. Pick any lowercase letter you want. And then you have a subscript. So this part here, the A in this example, that's your name of your sequence. So if you have 2 sequences, you don't both call them A and then a subscript. One would be like AN and the other one would be like BN. Now, the N down here is which term you actually are at in your sequence. So if you start your sequence at n equals 1, your first term would be when n equals 1, you'd plug in n equals 1 into your formula, and you should get back whatever that first term is. Now, this part on the other side of the equals, this is going to look like a function, except the domain will only be the integers that correspond to your sequence terms. Okay? Now, here's some extra terminology. If you start your sequence at n equals 1, then your sequence would look like A1 for the first term, A2 would be your second term, A3 your third term, A4 your fourth term, and so forth. If you wanted to be fancy and put it all together, these curly braces indicate you have a sequence. The n equals 1 on the bottom indicates you start with the index of 1, and the infinity on the top actually tells you keep going forever. If you ended before forever, you would actually say which n you stopped at up there in what looks like the exponent position. Note, this is a similar terminology that we did when we did the product notation, where we multiplied everybody together. The difference, instead of multiplying everybody together now, the curly braces mean you just put them in a list. Okay? And that's it. That's a sequence, or an infinite sequence. Now, turns out, while intrinsically people like to think first term start with n equals 1? You guys have all played with computers before. What do we know? We have a tendency to start our indexing actually at 0 because it makes our life easier. So same deal with sequences. Turns out that it's really, really common to start your index at 0, and your book right now does this for, I believe, all the sequences that he gives in your book. So much better than our last book. Our last textbook started everything at 1, and the formulas were just miserable for his examples. Okay. So if you start at 0, then the sequence goes as follows. You start off when n equals 0. Your first term wouldn't be labeled as A1, it'd be labeled as A0, then A1, then A2, etc. And notice it could be the exact same sequence, you just relabeled them with the n's, with your index. Okay? And that's the basics of the notation. Let's do one example, and then we'll pop back to induction. Okay? But any questions before we jump to our next example? And I say that because I'm not sure the next example is going to render correctly. I'm seeing no questions coming in, so I'm assuming you guys are okay-ish so far, crossing my fingers here. So, can you guys see this next thing? It should be a poll everywhere question. Yellow squares, lovely. All right, so what I'm going to do is I'm going to share something different with you guys, and let me pull this up real quick. Should have had this prepped ahead of time. All right. You should be able to see it now. And I'm going to stop sharing the other one. All right, so this guy here is just a basic sequence question. And what it says is you've got the sequence 1, 8, 27, 64, 125, and the pattern keeps going. And the question is seeing if you guys can figure out the format of that pattern. Okay? So for this guy, all of those formulas are what are known as closed formulas. In other words, you have an actual function answer here. Notice the difference between all of them is just a little bit of change in the formula, and you've got some of them that start at n equals 1 and some of them that start at n equals 0. So go ahead, give a guess, see if you can figure out which of those answers would work out. And let me go ahead and actually put this full screen so it's a little, whoa, should not have done full screen. Just a second. Sorry about that, covering up your answers, or covering up the page when that happened. All right, it looks like I got 2/3 of you to answer back. If we went and, where'd it go? Show responses. Well, we definitely have some agreement here on responses. It looks like everybody responded for the last 3 answers, and the last 3 answers all have cubes. So the question, of course, is, well, which one works? Anybody have a guess on how you can tell which one of these answers is going to work? Well, if you didn't have the answer choices, you'd have to come up with this yourself, and it probably would be easier to do that, or maybe not. But yeah, probably the easiest way to tell which one of these answers is going to work is just try to find that very first starting term. So our very first term in this sequence is a 1. These formulas all tell you you're going to start at n equals 1 or 0, so plug in the appropriate n equals 1 or 0 into all of the different formulas. Yes, the first 2 answers are definitely no's, so let's start at the bottom and go up. Actually, we don't need to start at the bottom and go up. We'll start at the middle one here. We'll be strategic today. So if you plug in n equals 0 into n cubed, what do you get back? So you get back 0. Is 0 our starting term? Or our first term? And everybody say no. So that means this one here actually won't work. Okay. Now if we come down to this 4th answer here, this one says we're going to start at n equals 1. Well, if we put n equals 1 into this formula, do we get back our first term? So if we plug in n equals 1, do we get back that first term? Yes, so that means that this is a possibility in terms of our answer choices. So far that's been the only one that's possible. Now when we move down to this very, very last example, if we take our n equals 1 and plug it into our formula, do we get back the first term? Do we get back that 1? Yep, so here we actually don't get back the number 1, we don't get back the first term. So just by process of elimination, the only two answers that would give you back 1 for the first term is the second answer and the fourth answer, so n squared and n cubed. N squared is obviously wrong because these guys are all cube numbers. Okay? So turns out the only right answer right here is actually going to be, well, that didn't work so well. That answer would be the one that would be right there, by that fourth one. Now, just as a caveat, this last one here actually is a correct formula for this sequence. And everybody disbelieve me right now because we just showed it didn't work. If, here's the adjustment, you started at n equals 0. Yep, you got it. So what happens if you decided a different index? The formula will change, namely your n will be switched with an n plus 1 or n minus 1, depending on how you changed your index. So that's something that we're really not going to deal with in our course, but it is something that comes up a lot if you deal with sequences in the future. So what I will probably do is give you guys some extra resources about sequences in case you need to deal with them in the future, and you'll have access to our Canvas course indefinitely, as long as you have access to Canvas. Okay? So that's the crash course on sequences. Questions so far? If not, we're going to go back to the induction question. All right, I am seeing no questions come through on sequence, so feel free to change that in the future. But let us go back now to induction. All right. So we ended here on induction, on this induction example, where we had an example that said, suppose you have some sequence. Make sure my pen is going to write. And the sequence was given like that. Now this is a little bit different format than what we did previously, so let's first of all write out what this sequence looks like. Okay? So what this tells us is, it tells us that your first two terms of the sequence are going to be 3 and 2. The sequence is going to start at 0. That little squiggle was trying to be a 0. So starts at n equals 0. So A0 is 3, A1 is 2. Now if we want to get to the next term in the sequence, this would be A with a subscript of 2. I don't actually have listed out A with a subscript of 2, so this is where you actually have to go back to the formula. And this formula right here, I didn't write it down, but often you'll see it saying, hey, use that formula up there when n equals blank and above. In this case, 2 and above. So n equals 2, we'll plug in n equals 2 into this formula right here, and let me highlight the formula so it's easy to see. So we'll have 3 times a, and a subscript is n minus 1. Well, if n is 2, 2 minus 1 is 1. And then plus 4 times a to some subscript. This subscript is n minus 2. Well, n is 2, so 2 minus 2 is 0. Notice what this tells you. This tells you we're going to plug in the previous two terms of the sequence. A1 is 2, and A0 is 3. This is what's known as the recursive form, or the recursive relation, or the recursive formula. That last word can change depending on who says it and what book you're using. Okay. So then we just need to actually figure out what this number is. So we've got what? That looks like 6 and 12, so that looks like an 18. Now, one more. So A3 would be 3 times A. Well, n now is 3. So when we plug in n equals 3 for the new subscript, we'll have 3 minus 1, or 2. And then plus 4 times a with the subscript n minus 2. Well, n now is 3. 3 minus 2 is 1. So we'll have 3 times something plus 4 times something. And notice those are the previous 2 terms in the sequence. So A2 was the one we just found, the 18. I am so regretting doing this one now. And A1 we found previously is 2. So 3 times 18, 3 times 8 is 24. So that should be 54. And then 2 times 4 is 8. So add those together and we should get 62. Please double check, make sure that I actually got the right number there. So that's what your sequence would look like. So you'd start off, you'd have 3, then 2, then 18, then 64, and it would keep on going. Now, I didn't write these guys here out in a list along one horizontal line just because we had scratch work. So here I just wrote it vertically stepping down so we could write in the scratch work. But still, that's the idea for what we mean here. Now, we haven't done anything in terms of an induction question yet. So let's go ahead and put in the actual question. And I'm going to write it in green again to indicate the green's the question, the black's the work. So here's what the actual induction question is. So show by induction that the formula for this sequence can also be written as an, or the nth term, is 4 to the n plus 2 times negative 1 to the n. And that's supposed to work for every single one of your terms, n equals 0 and up. So notice format-wise, this format is exactly the same as the examples that we looked at when we were doing our little baby crash sequences. This is what's known as the closed form. It's what? Looks like an actual function. There are no previous terms whatsoever. So let me actually make a note of that. This guy is what's known as the closed form, and it actually looks like a function. Up here, this guy is what's known as your recursive formula, or recursive form, and the recursive there is what? You guys know what recursive means. It means you used a previous term or a previous thing. Same use of the word recursive here as in programming. Now, every sequence can be written in its recursive form as well as in its closed form. So this question is simply saying, you know what the sequence is. I gave you the recursive form. Now I just need to verify that somebody else found the right closed form. And our next section, the section that we will hopefully get to at least a little bit today, and then on Monday, is where we're going to have a procedure of where we find this closed form. So that's what we're bridging into. The induction is going to show that if somebody else or yourself did the procedure to get the closed form, that you didn't screw up in any of the math, you actually verify that, yes, this is correct. Okay? So that's the setup of the question. We still haven't done any induction stuff yet, so let's go to the induction. So anytime you're dealing with induction, you're going to start off with your basis step. So first thing, basis step. Now, I'm going to claim that in this particular example, we're actually going to have to check the first 3 n values. Okay? And I'll tell you why here in just a second. Actually, we're going to do it just now. So what we're going to check is we want to check that our sequence actually and truly meets this formula, or adheres to this formula, or makes that equals right there true. Okay? So if we look at the very first term in our sequence, this is when n equals 0. Well, if n equals 0, we get for an would be a0 or 3. So that would be our left-hand side. And in the formula, 4n plus 2 times negative 1 to the n, plug in 0, you'll get 4 to the 0 plus 2 times negative 1 to the 0, or don't overthink it, 1 plus 2, which is 3. Those two guys are exactly the same, so we're good to go. Note, you could have also just gone ahead and plugged in 3 on this side and n equals 0 on this side, and you would have got that both sides were equal. That's also totally fine as well. Now, We have to do this one because basis steps always start at your smallest n, but notice where our 3 came from. Our 3 was actually given here as one of the terms that was straight up given to you. We haven't touched the form up here, the recursive formula, so we have to actually get to where we've dealt with one of the terms in this recursive formula right here, namely the smallest one. So notice we're going to have to build up all the way up to n equals 2. So the next thing that we're going to do, I hate resizing this for you guys, I'm sorry, but we need to see that top thing. So n equals 1 will be next. So here on our left-hand side of our formula, we're looking at an. Well, n equals 1, so that's a1. That was a term that was given to us, or a 2. If we then look at the right-hand side of our formula, and again, our formula that we are looking at is, that's the formula we're trying to prove. So if we look then at the right-hand side of that formula, we're looking at 4 raised to the n plus 2 times negative 1 raised to the n, but now our n equals 1. So this is 4 plus 2 times negative 1, or when you simplify that, it is, of course, 2. Notice so far, both of these two guys were given. They were your, what's known as initial conditions, or your initial terms. So we haven't yet gotten up to that recursive formula yet. So one more term and we'll get there, and that was too far down. Need to actually still see that. All right. So n equals 3. I lie. N equals 2, the next one. So left-hand side, we have a n equals a 2. Now we already computed a 2. It was right up here, that 18. And we used it by using our recursive formula. In other words, we built it from the previous 2 terms. So that means, yes, we've now grabbed that last recursive formula that we care about. So bam, we've now hit all 3 pieces of information that we were given. Okay? So this is the last thing that needs to be included in your basis step. Then we just need to check to see if 18 actually works for the formula. So then we look at our formula, so that's the right-hand side here. So we have 4 to the n plus 2 times negative 1 to the n. Here, n is 2, so this would be 4 squared plus 2 times negative 1 squared, or 16 plus 2, which luckily is 18. I shouldn't say luckily, I actually built this question knowing that that should be the answer. Good so far. You guys okay with why we needed to do all 3 of those basis steps? All right, I'm not seeing any questions coming in so far, so I'm going to assume you're okay with the basis steps. Here, key thing is you want to make sure that you've taken care of each one of your pieces of given information. So we had 3 pieces of given information. That corresponds to 3 basis steps. Now, next thing that we have is we're going to be looking at our induction step. So the first thing in our induction step is we assume everything works for n equals k. So here we will assume, and do I need to do any background for us here? Yeah, we're good. So assume k equals 4 to the k plus 2 times negative 1 to the k. And that would be for any k that you want as long as the k is 0 or bigger. Okay. Notice that is exactly the same thing we would have done last time in regular old induction. Literally, you just take the formula you're trying to prove. So I boxed it on purpose because there are 2 formulas involved in this question. So this is the formula we want to prove. We just changed all the n's to k's. Now, this guy is going to end up having to use strong induction. So I am on purpose going to leave a blank here. And we're going to go back in and fill in the stuff we're going to have to worry about. So now we're going to show that this formula works for n equals k plus 1. Okay? So we start off and we say, all right, well, let's look at our term that is, well, when n equals k plus 1. So this will be a subscript of k plus 1. Now, what do we, wow, that was terrible. Let me try n equals again, just a second. Can't over scribble on this, it just gets a mess. Now, what do we know for sure about this k plus first term? Well, we know that, and we know what we want to get to, so we'll do some scratch work to the side here to show what we want to get to. So here is our goal. We want that this k plus first term actually equals 4 raised to the k plus 1 plus 2 times negative 1 raised to the k plus 1. Notice that is exactly our formula that we have up here, except we replaced all the n's with k plus 1. So that's our scratch work to tell us where we're shooting for, and specifically, how do we know when we're done with all the algebra. Okay. Now, I'm going to do a second little thing, and the second little thing is just to remind ourselves what the formula of the sequence was, because it's way back up here. So A3 and then A4. So our formula for our sequence is AN equals 3, AN minus 1, plus 4, AN minus 2. Okay. Now that was given. Okay. That's that formula in black right there. That was what we were told we had already with this sequence. This is something that we know for sure. We know that works for all n's, well, as long as n equals 2 and bigger. Okay. So here, I'm going to say, you know what? We already checked this for our basis step when n equals 0 and n equals 1 and n equals 2. So we're actually going to go ahead and assume right here that k plus 1 is 2 or bigger, which if we write it in terms of k's, that means k is 1 or bigger. So I'm going to just write that down here in a subscript. Now, why would I have said that at all? I said that mainly so we know that this recursion formula, this formula that we were given, works. Okay? If you don't do this part here, no worries, but what you do have to remember to do is this. Okay? So we want this to happen when n equals k plus 1. So everywhere there's an n, we're going to replace it with a k plus 1. This side's already done. So then we have 3 times a with a, and what's the subscript on that first a? Anybody got what that subscript should be? N equals k plus 1, and we want to subtract 1 from it. It would just be k because you subtract 1 from k plus 1, and you'll get rid of that plus 1. Now, the next subscript over here is going to be k plus 1 minus 2, because we have n minus 2, and n is k plus 1. So it's k plus 1 minus 2. Anybody got that? It won't be k, it'll be k minus 1. Now, here's what we know about these guys. These are previous terms, and what do we do in our induction step? We're always trying to replace something we don't like with a formula we already know works. So we already know right here that our kth term equals 4 to the k plus 2 times negative 1 to the k. Anybody have a guess of what we could or what we want to plug in for this next a with a subscript k minus 1? I know it'd be complicated to type it, but any guesses of where we would look for it? What would we want to plug in there? What would be your gut reaction? I'm going to assume some of you might be typing. Oh, there it comes. Yeah, so gut reaction here is typically you want to take the same formula that we care about and just replace all those k's with k minus 1s. Or take our goal that we wanted to and replace all of the n's and have the k minus 1. Yeah, repeat the previous process, but have the k minus 1 involved. And that's exactly what we're going to do. So here we'll have 4 raised to the k minus 1 plus 2 times negative 1 raised to the k minus 1. And here's the fun step. This is how you know it's strong induction. That. With regular old induction, you actually don't have that k minus 1 term verified. All regular old or weak induction does is verify the situation when n equals k. It didn't verify anything. Regular induction doesn't verify anything but your basis step and when n equals k. Strong induction says, don't be stupid. Of course, if we verified up to n equals k, we would have verified everybody between the basis step and n equals k as well. So of course you can use that thing that you wanted to use. So if you ever have to use more than one previous step, this is the guy that makes it strong induction. Or type 2 induction. That's it. That's literally the only difference. Notice you do exactly what you expect you should have done from regular old induction, except regular old induction just wasn't worded the same way, the right way to do what you wanted to do. That's literally the only difference. Now, if you want to be very precise about it, here's the precision. So up in the assumption step, where we assumed everything worked for n equals k, we're also going to assume it works for n equals k minus 1. So and. So 4 raised to the k minus 1 plus 2 times negative 1 to the k minus 1. And then you keep on going all the way down to your basis step. And I'll go ahead and write out the basis step. Your basis step here is a0 equals 4 to the 0 plus 2 times negative 1 to the 0. That is literally the only difference here between the strong and the weak induction, or if you prefer, the type 1 versus type 2 induction. It's literally just those bits I just circled. And that's it. Everything else is going to be the same as before. Okay. So let's finish this guy off. So here, what do we want to get to? We want to regroup these 4 terms so that we actually have 4 raised to the power k plus 1, and then 2 times negative 1 raised to a power. So let's go ahead and group those things together. So we've got 2 terms with 4 raised to some power. So this first one out here is 3 times 4 to the k. The second one right here, well, that 4 multiplies by the 4 raised to the k minus 1. And what happens to the exponent if we actually add those 2 guys together? Or I should say add, multiply those 2 guys together. What would be the new exponent on the 4 from this term? Anybody got that? Yep. The new exponent would be k because we just added 1 and k minus 1, which means these first 2 terms right here, when you add them together, you'll have, well, 3 of one plus an additional 1 of the other. That's going to be 4 times 4 to the k. Now, the second 2 terms came from where we've got the negative 1 to the k and negative 1 to the k minus 1. 3 needs to be multiplied in, like I almost forgot right there, and 4 needs to be multiplied in, like I almost forgot right there. Actually, I did it wrong, so let's correct that. 4 times 2 is 8. Don't need the extra factor of 4. Now, putting this together, let's go ahead and add these guys. This one is really 6. So here we'll have, all sorts of fun things. We're going to have to be a little bit fancy with that one. So we have 6, negative 1 to the k, plus 8, negative 1 to the k minus 1. And we'll do something fancy with that guy in just a second. So we'll do a little scratch work to the side to get the fancy step. Now, first term right here, the one with a 4 to the k, that simplifies to what? Well, we can do the same thing as before. It'll be 4 to a new exponent. So add the 1, add the k, and we'll get 4 raised to the k plus 1. And that totally gets us to that first term that we wanted. Remember our goal over here We wanted 4 raised to the k plus 1, so we're there on the first term. Now, second term, this is where things get a little more interesting. And there's a bunch of different ways that you can do this. You can be super fancy, you can be less fancy, you can be more working with exponents. How much work would you guys like to do? As little work as possible? Or would you like to make it not a fancy method and just have all the middle steps? Because I can do anything from being very pedantic to being a little bit fancy, and there'll be fewer steps if we're a little fancy. So fancy or not fancy? Anybody got a vote? Ooh, I like these votes. All right, so scratch work then. Here's the thing to know. -1 squared is what? Don't overthink it. Awesome. -1 raised to any even power, regardless of whether it's a 2, a 4, and 1,872, is still going to be 1. What happens if your -1 is raised to any odd power, though? Correct. So that would be when you have the -1. So what we want to jump to is we want to jump from this -1 raised to the k, or k minus 1 exponents. We want to jump up to k plus 1. So here's the extra fancy part. K plus something needs to equal k plus 1, and k minus 1 plus something will equal k plus 1. And that should be the last fancy bit of info that we need. So you add 1 to k to get k plus 1. And what would you add to k minus 1 to get k plus 1? What should go in this last blank over on our scratch work? So that one will just be 2. Right? So here's the fun fact. These guys that we just did, this last bit here, the k plus 1 and the k minus 1 plus 2, these are dealing with our exponents. So we're going to insert things that we want. Oh, I did not mean for that to be red. Just a second. We will do red in just a second to indicate new things, though. And we're going to do this term last, so I'm going to leave a big blank. But for this term with the 8, this is -1 raised to the k minus 1. I'm just going to multiply it by -1 squared. Remember, -1 squared was what? It was regular old 1. You can always multiply any term by regular old 1, and it doesn't change anything. That's the weird and fancy thing about -1 raised to an exponent. So we just inserted this one, no worries whatsoever, because it still equals 1. Now, here's where we actually have to be a little bit fancy. So we had 6, we had -1 to the k. We only want to include one extra copy of our -1 raised to a power. Unfortunately, if you do that here, it will change the sign. So we're really going to still be multiplying by -1 squared. With that new -1, we're going to group it with the coefficient. That's the fancy part. So putting this all together, we'll have 4 raised to the k plus 1. We'll then have -6 times -1 raised to the k plus 1, plus 8 times -1 raised to the k plus 1. Those two will combine. Notice they both have a factor of -1 to the k plus 1. And what would be the coefficient now when you add those two together? Well, you would just add your two coefficients together. So you've got -6 copies of the -1 to the k plus 1. And you also have 8 copies of that -1 to the k plus 1. So when you add the -6 and the 8 together, you'll get your 2. And quick check, is that the formula that we wanted? Did we reach our goal? What do you guys think? Did we reach our goal? Ooh, I see answers. You were right. Yep. So we reached our goal, this guy here. totally matches this formula right up here. So what does that mean? Bam, we've completed our induction step. Now, not going to lie, anytime you have one of these sequence guys, it's always going to be strong induction as long as you have in your recursive relation at least 2 of the previous terms. Notice right here, we had 2 previous terms, so this tells us we're going to have to do strong induction as soon as you have that second previous term. This one here was actually more fancy than what they often are because of the -1. I forgot to check for that before class, but hey, you got to see the complicated version. In the examples of sequences that you've got on your homework, if you choose to work them, they are simpler than this. You still have the same structure where you would plug in n equals k plus 1, but the algebra is much easier. Now, once we get to this conclusion, that is exactly the conclusion we want to have happen, which tells you what? It actually tells you that this original thing saying that our sequence actually had this closed formula, this formula that looks like a function, that formula is true. So let me make this not have weird spacing issues like we found out happened last time. So last thing is conclusion. The formula or the closed form for this sequence is that thing we were told it was supposed to be at the beginning, 4 to the n plus 2 times -1 to the n. Induction is crazy powerful. Not going to lie, though, there's definitely a big chunk of algebra right there involved typically. Some of these guys, some of the guys will only have 1 or 2 steps that you combined, the ones that we've done together in class, so sort of mid-level induction step in terms of the more algebra that you need. One of the reasons I try to give you a bunch of different examples so that you saw some of the different things that we have a tendency to pull from algebra. So what we've done, if you look both at what we did on Tuesday and today, and also those pre-recorded videos for you guys, you've got pretty much every single example of induction that you will see for our course. The only thing you'll see new in the future is probably just different numbers. So you've got some sort of pattern there. And yes, extra resources too if you find you get stuck with algebra. Okay. Questions kind of make sense, and other than the freak out of remembering your algebra skills, makes sense at least if somebody else is doing it. All right, cool. It looks like most of you are somewhat agreeing. If you do run into questions with this stuff, feel free to contact me, grab me, etc. I can't remember if I told this to you guys previously or not, because I don't remember when I set it up for you guys. But I did go ahead and set up a Discord channel for our course. So if you guys want to use it to either ask questions for me or talk with each other about various questions, definitely take advantage of different things. I think I told you this last time. It was my other class today that's new. But anyway, that's all I got for induction. So unless you guys have other questions, the rest of today is just bumping in to talking about sequences, and based on time, we'll do order 1 sequences today and then order 2 sequences on Tuesday. All right, I am not seeing any questions from you guys, so I'm going to go ahead and bump us into dealing with sequences. So we already had our crash course on the basic terminology of sequences. Let's now talk about, if you have a sequence, how do you go about actually computing its formula? Now, I'm going to skip the thing where you're just given the list of all of the terms in the sequence. I'll post some notes if you want to look over it, but for this semester, we're going to be focusing on, suppose somebody else already told you, actually, in the first couple of examples, we can do that. So let us grab a first example. Suppose you have the following guy. So sequences. Suppose you have the sequence 2, that was trying to be a 2, sorry about that. 2, 5, 8, 11, 14, and so forth. Anybody notice a pattern with that particular sequence? What does it look like you're doing to get the next term? Yeah, and it's really straightforward to see. That was so trying to be a 2. That was definitely, that first term is trying to be a 2. It's the worst 2 in the world. So here, each time, we did what? We added 3 each time, and that works just fine. In these type of sequences where you add the same thing to each term, they're called arithmetic sequences because you added something. I don't care if you remember that term. Okay? So what this tells you is you took the previous term, the a with the subscript n minus 1. It tells you previous term. And this just tells you, hey, to get the next term, you took previous term plus 3. And that's literally it. Now, in one of these recursive forms, you do have to decide where you want to start. So our first term is 2. And I'm going to go ahead and force us into starting at 0 here, just because it's going to make our life the easiest. Okay? And here, to name this, this is our recursive formula. Now, suppose you want a closed formula. Okay? Now, the closed formula is what we were working on in our last example with induction. It's a formula where you only have the n's involved. If we wanted to find the 100th term here you'd have to go through the previous 99 terms and keep adding 3 each time. The closed form, the one that looks like a function, you just plug in whatever the index is, and bam, out comes the term. Okay? So that's the most desirable guy. So in this particular case, if you want to convert from the recursive form to the not recursive form, there are 2 main ways to do it. One of them is a strategic way of guess and checking. Okay? I'm going to skip out on that way today and show you what the actual formula is. If you're interested in that strategic way of guessing, which works in almost all, I shouldn't say almost all, many, many sequences, it is actually already posted on Canvas in our section that says background for sequences and matrices. And I think this exact question is actually worked on that one. I'll show you how to go through that procedure. Instead, I'm going to give you a formula here. So here's our formula. The formula for arithmetic sequences says the following. That was trying to be a U, sorry about that. Suppose you have the arithmetic sequence, so you have an an minus 1, and then plus. Your author doesn't call it this, but standards here are to use a D for difference. I see the question that came up. I'm going to say almost. Hold for a second. There's one issue with the formula you sent in. And here, this formula that we're going to have does assume that you start at 0. If you start at 1, the formula does change a little bit. Okay? So the closed form then is going to be your leading or your first term. That's a D, not the first term. So just a second, get rid of the D. It's whatever your first term is, so your A0, plus whatever that difference was times n. And this would then be the formula corresponding to n equals 0. So if we go ahead and apply that to our situation, this would be almost exactly what a couple of you guys have sent in. It would be, well, what? Our first term is 2. Okay, so I'll write this over to the side. The horrible looking 2 from above. And what's our D? You guys already told me it. It was the plus 3. If you subtract 3, you'd want the negative 3 over there. And then, so what would you do? You'd do 3n. And that's literally it. Okay? That's it for arithmetic sequences. Questions? Make sense? Kind of feeling okay? Notice, why does this work this way? This n here tells you how many copies of 3 you had to keep adding. And that's it. It's literally it. So the other common type of example that you see, and let me actually make the example title slightly different color, is what's known as geometric sequences. If you are either in or have already taken Calc 2, you would have dealt with geometric sequences, or really series more there. This is the same thing, but the sequence, the list of numbers. So this guy here is 3, 6, 12, 24, 48, and it keeps going in the same pattern. Anybody have a guess on how you get the next term from the previous term? In other words, what's the pattern going on? Anybody spot a pattern? Yep, so the pattern here is you multiply by 2. So geometric means you're just going to multiply each term by the previous. Multiply your previous term by a constant to get your new term, which is totally what's going on here. Which means if we write our recursive formula, this guy is, let's see, P's and R's are common. Let's go with R. R for ratio. And P technically for row, also Greek letter for ratio. So I'm going to go ahead and assume here that n starts at 0. So if n starts at 0, our first term, A0, would be 3. Again, that's just going to make your formulas a lot easier to deal with. So let me go ahead and put the formula in for geometric. And anybody have a guess on what the formula might be? Oh, wow, I messed up. Just a second. I jumped ahead to the formula. Sorry about that, guys. Anybody spot why I erased the stuff that was back in black here? What should that number actually have been? Yep, that number totally should have been 2. Why? Because we actually care about the actual sequence we had right there. And in my head, I was already jumping to the formula. Sorry about that, guys. So if we related the general formula that has an R in it back to our specific formula, notice the R here would be that 2. So putting this together, the actual closed formula, or the formula that looks like a function, is going to be your very, very first term, so A0. Then you do what? Well, to get the next term, you multiply by, in our case, we multiplied by 2. So we're going to multiply by whatever that number is, this R here. And you're going to do it a bunch of times. Well, if you start with an index of 0, it turns out the number of times that you're going to multiply it by is n. If you start at index 1, it turns out the exponent there is n minus 1. So let's apply this. What would be our closed form for our specific example? Our 3, our 6, our 12, our 24, etc. What should I write down for our formula there? The thing that looks like a function. Anybody got a guess? We'll definitely have a 2 to the end. There's one missing part. Anybody got what the missing part is? Yep, perfect. And here's the key thing, especially if it's been a little while since you've been doing algebra. You'll almost always have some coefficient times in exponential form. Don't multiply the 3 and the 2 together and write down 6 to the end. Please don't do that. 2 separate things. Okay? I see that every so often. Hopefully not too much this time. All right? So that would be the answer right there. That's literally it. So that's a geometric sequence. Geometric sequences are awesome. Arithmetic sequences are awesome. Not going to lie, they're not the most frequent things you see, but at least in order 1 they are. And when I say an order 1 sequence, that actually refers to the recursive form right here. It means the order 1, the 1 part, means you've only used one previous term. We're actually mainly about to focus in order 2 sequences. And let me go back to our example we had just a second ago. This guy right here, where'd it go? This guy right here that's highlighted in yellow, that's an order 2 sequence because you have 2 previous terms. Typically, with order 1 guys, you could almost guess and check and get everything right there. So let's do one last situation of order 1. And at that point, we'll be done for today, and next time we'll look at the order 2 examples. So suppose you have the following guy, and I'm going to go ahead and give this example in its closed form. Not closed form. We're trying to build to closed form, recursive form. So this guy here, its recursive form is given by an equals 2an minus 1, so almost the same as what we had previously, but we're going to subtract 1. And we're going to start here at 5. So, first of all, let's go ahead and look at what the actual sequence is. This tells us if we actually write out the sequence, it would start at 5. The next one would be 2 times 5 minus 1, or 9. Next one would be 2 times 9 minus 1. Notice it's 2 times previous minus 1. So that's 18 minus 1, that's 17. Next one is 2 times the previous minus 1. 2 times 17 is 34, so this is 33. And I'm totally going to stop there because I don't want to do the next one, although technically it'd be what? 65 if we wanted to. So I already said it, I might as well write it. So 2 times 66. Now, what do we want to do? We would like to find the closed form, or the closed formula, or the recursive relation, as your book typically calls it. And remember, your closed form, this is the one that it actually looks like a formula. It looks like a function. It actually is a function whose domain is integers, where all your indices live. Now, notice this formula right here. It's this 2 times previous term minus 1. Is this guy either an arithmetic or geometric sequence, like what we had with the past 2 examples? What do you guys think? Does it look like either arithmetic or geometric sequence? Arithmetic was the one where you just added something. Geometric was where you just multiplied a constant. What do you think? Could we use either of those previous 2 formulas? We could not, correct. And that is because the previous formulas are either only adding a constant or only multiplying, and you're right, this is where you've merged them both together. So this is properly a different format. It actually turns out your arithmetic and geometric sequences are in fact specific cases of the more general form. So let's go ahead and give the general form here. Okay? So here's the general formula. And I'm going to match these symbols with what your book says. Your book uses S and T's, which are not standard at all. So it says if you have an order 1 recurrence relation, so you have this recursive form, and it's only using one of the previous terms, you can totally have a coefficient on the previous term. You can also totally have a coefficient on the end. And this is, I'm going to use a term that if you haven't heard it before, don't worry about it. If you have, this is going to be a tie-in with other math. This is what's known as a linear equation. It's linear because you don't have your previous term raised to any exponent or on the bottom of a fraction or in a square root. Okay? It's just being multiplied by a constant, maybe being added to a constant. We're going to go ahead and assume that it starts at n equals 0. The formulas do change if you don't start at n equals 0. And then in that case, your closed form, your actual formula that you have, is going to turn out to be some constant C1 that you'll have to solve for, times s raised to the n, plus some other constant C2 that you'll have to solve for. Now, caveats. The caveats here are s is not allowed to be 1. So where S cannot be 1. If S equals 1, cover this S up right here, and it's just arithmetic. We've got a different format. If T equals 0, you actually have geometric, so you use the other case. So this would be the situation where you actually properly have something added, and it's not arithmetic, so you actually have something other than a 1 right there. And that would be your formula. So for this guy, let's plug it in. Our S would be 2. Our T would be -1. So when we go ahead and plug this in, notice T actually isn't part of the formula at all. Oh, that was too far. We'll get that AN equals some C1 that we have to solve for times 2 to the n plus some C2 that we're going to have to solve for. And it turns out when you solve for these guys, you would actually take the first 2 terms in the sequence. So n equals 0. First term would be 5. So 5 equals C1 times 2 to the 0 plus C2. And n equals 1. The second term there was 9 equals C1 times 2 to the 1 plus C2. You'll solve for C1 and C2, and I'm just going to give you what they are since we're out of time. C1 would be 4, C2 would be 1, which then tells you that your final answer here is 4, that was trying to be a 4, times 2 to the n plus 1. And that's it. That's how you would deal with any of these order 1 guys. So that's it for today, because we're totally out of time. Next time we'll look to see what do you do if you have more than 1 previous term involved in your recursive form. But that's literally it for today. If you guys do come up with any extra questions, feel free to contact me between now and then. But unless you have questions, like I said, that's all the new stuff for today.